Okay, thank you. Thanks everybody for being here, even though there was a slight change of timing. And thanks for setting up the recording so promptly, actually. Thank you. Okay, so today's class will have two parts. So the first part will be the end of the proof of the identification of the Poisson boundary that I mentioned yesterday. So without moment conditions, but with entropy, finite entropy. And then the second part would be somewhat distinct. We will give a proof of the theorem that we announced in the first day about singularity of harmonic measures for certain random walks on some co-compact Fuchsian groups. So that would be some sort of a new subject in a sense. So first, let's see this discussion about the identification of the Poisson boundary. So recall that we start with the G hyperbolic group. So hyperbolic group, mu is a measure. And so then, of course, we have boundary of G is the Gromov boundary. And so what do we want to prove? Well, recall that we have this notion of entropy. We have that we have the conditional entropy of the partition that yesterday I called AN. And so the goal is to show that this conditional entropy divided by of the n step of the walk divided by n goes to 0. So recall what is AN is. Well, AN is just simply given by the partition of your space. So your reference space is the whole path space for the random walk. So this is a path space. And well, we just declare two sample paths, Wn and Wn prime, to be the same according to this equivalence relation. Well, it's just if the n step is the same. That's it. So, okay. And so what is the picture that we had in mind? So this would be the, say, Cayley graph of this hyperbolic group. And we know the random walk converges to some boundary point. And so clearly this determines this geodesic. And now the goal, once again, is to determine the location of the n step of the walk. So given the boundary point, how well can you determine the location of the n step of the walk? So this was the general question. And this is a precise quantitative way to say that. That if this is true, means that you can determine the location of the walk sufficiently well enough that the actual boundary that you have is not just the geometric boundary, but it also the probabilistic boundary. Okay. And so recall that we described this idea of a pin down partition. Pn. And the goal was to show two things. So it's a partition that we add. So if we're given psi, we can also maybe measure some other things about the walk. And this other information is contained in this partition Pn. And so we want to show two things. The first one is the entropy of, the n step of the walk given this additional information and also given a boundary. You can also put the boundary there, but let's write it like this. So this is small o of n, so it's sublinear. And this we already more or less gave the proof yesterday, but we will revisit briefly. And the second one is to show that the information that you added, so this is like, this Pn was additional information. Well, it's not too, it's not too much in the sense that the entropy that is contained in this additional information is still sublinear. So we can And from these two things, it follows more or less formally from just properties of the partitions and the Jensen's inequality that we get that one. Okay, and then, okay, so what is the construction of Pn, which we gave yesterday? Well, there's three things that we can say. The first information we want is pivotal times. So again, this would be our caricature sample path. So recall that we split the time in a bunch of intervals. So we introduce various constants. M is a constant which is depending on the hyperbolicity constant of the group. Alpha will come up now, and L come up when we talk about distances. So there are three constants. So we define these intervals, these chunks of intervals, I, K alpha. Well, just the interval of times between, of size alpha. So alpha K minus 1 to alpha. Yeah, sorry, alpha K, yeah. That's right. Okay, and so these are the intervals of times. If you can visualize it like that. And the random walk does a bunch of stuff, but eventually it might hit a pivot. So P1 would be a pivot. And then we do another thing, and eventually maybe we get another pivot. And then it does a bunch of bad stuff. And maybe here there's no pivot, and then you come back, there's another pivot. And then the walk can do some very weird stuff. And we'll go to Wn. So here is just recalling the times of the pivots, which we call Tn, which depends on alpha, so tau1, Tn over alpha. There's n over alpha such intervals. And so if there is a pivot, we record the time. If there's no pivot, we put some character like -1, some placeholder character just to distinguish it. It could be that there are no pivots. So recall that an interval, ik alpha, is good if there are two things. One is there is a pivot. And the second, that the steps of the walk are never too big. So the distance between wj minus 1 and wj is always less than this other constant L for every j in this interval. Okay, so for pivotal times, we do this. And now the second information that we want to record is the so-called good distance. And so this is dn alpha L, and this is just the distance between consecutive pivots. And you want that both are good. To have the pivot. And so we just take the actual distance between consecutive pivots. In this case, maybe you have only this guy, because the two pivots are not consecutive. So in this case, it's particularly bad situation. We have only one pivot, but okay, in general, you will see that there will be pivots. Okay, and the third thing is to encode the bad intervals. And this, in this case, we record everything in the bad intervals. We record all the increments in the bad intervals. So we have what I call B, K1, BKS. S is a number of bad intervals, and BK is GI, where I is in the union of the previous interval, the current interval, and the next interval. So, yeah. So these are the three things we record. And so yesterday we gave almost the proof of the first thing. So the two important propositions that we need. So proposition A, let's say, is that the entropy of the walk, the end step of the walk, given all the stuff, so given Tn and Dn and Bn, so given all these amounts of data, is sublinear in N. And so P will be just the join of all these partitions given by all these variables. Okay, and so the proof of that is as follows. So here's the picture. So the picture maybe we can call P last the last pivot. So we need to do two things. Either, so we need to recover the last pivot first, and then we recover the walk next. Okay? So how well can we recover the last pivot? Well, we did the discussion yesterday about this. The thing is, since we know the distance between good pivots, the good distance, and all the increments in bad intervals, we know, what do we know? We know the distance between the origin and P last. So let's say in this case, P last would be this guy. So how well do we know this? Well, we make an error. At every time, we could make an additive error. So there is a bit of an error that you can make in determining the distance between this and that. But the error is not too bad. So because how many pivots do we have? Well, we have n over alpha are the number of pivots. Okay. And then there's a constant, which may be something like m, some constant that depends on the hyperbolicity to tell you how far you are each time. Okay? And so how many possible locations there are for the last pivot? Well, again, we know this distance up to q plus or minus m n over alpha. So there are m n over alpha of those. And then, okay, the pivot is in an M neighborhood of the geodesic. So you also have to take that into account. But that's basically, it's in a ball of radius M around the geodesic. Right? So, okay, so the number of choices for P last is at most, well, it's basically N over alpha times the cardinality of a ball of radius, I don't know, 2 times m, something, which is still m, something like this. So is that good enough? Is that good enough to tell you? First of all, well, we still haven't figured out exactly Wn. We only figured out the last pivot. But okay, once we know the last pivot, we know Wn. And that's because we assume by definition that the last interval will be bad. So we record, since last interval is bad by definition. I didn't write it in the definition, but we always assume that. Well, we once given P last, we know, we know the last bit. So this last increments are also recorded. And so we just multiply P last times the last bit. We know Wn, which is just P last times, I don't know, G, I don't know, G big T, something up to G N. So let's say, right. So let's say the big T is the last. Yeah, let's say that this is G T and so forth. Yeah. So we know everything, so we can record. So the number of possible choices of Wn is the number of the possible choices of P last. And so the entropy of An given this partition, we will call Pn, well, is at most the log of that number of n over alpha times the cardinality of the ball of register. Because remember that the entropy is the upper bound for the entropy is the log of the cardinality. So that's it. Can you still follow the proof so far? Yeah. So that's it. So for this part, so we did prove this part of the lemma. Now the second thing will be to show, yes. Yeah. Very, very good question. And you have to use the WPD condition. You have to, if you have an action on a locally infinite space, this is not true for every action, but you have to use the WPD condition precisely because once you know P last, you have a bunch of options for that. And I forgot exactly, but you look at 2 points, and you know that once you determine the locations of 2 points, then really there's only finitely many options. So it's a slight modification of this, but you need to use the WPD condition, of course. Otherwise, it's not going to be true. Yeah. Very good questions. Any else? Okay, so now from here, we can finish with the second lemma, which is also not extremely long. Okay, so if we really want to be precise, there's some quantifiers, which since I've so far given all the quantifiers, maybe we can still say it. So we said the following, that if mu, yeah, in fact, here mu again should be an alternating measure to be precise, but let's gloss over this. So if mu has finite entropy, then, okay, for every epsilon, there exists some alpha naught, such that for every alpha bigger than alpha naught, there exists L, okay, such that. So you see that here we have these 3 constants. Yeah, so M is fixed by the geometry, then we choose alpha, and then we choose L. And the actual statement is the limb sup. So it's not quite true that this entropy is sublinear, in the sense that what is true is for every epsilon is the growth rate is less than epsilon. So okay, you can say that sublinear, but it is a bit weaker than say it's log n or something like that. Yeah. So for every epsilon, we have to adjust the constant to get this linear rate down. So, but it's fine if you. Okay, so again, here we forget about the geometric partition. Here we're really just looking at the walk as globally. Like, if I give you this information, is it too much information? Does it have too large of an information content, or it's maybe enough? And recall that if we did it with the distance, okay, you see the thing is the distance is just a positive integer. So it's not a lot of information usually, especially if you have a bound on how big this integer can be. It's much, much less than given the whole path. Of course, annoying thing, which we really need to check, is this part, where we have all the bad intervals and all the increments. Of course, if every if every interval was bad, This would be a big problem because this would be the entropy with the whole walk. And then you would have certainly positive entropy. And the Goswami theory of pivots indeed precisely shows you that you can bound this entropy. Okay, so what is the lemma that we need from Goswami's theory, which, okay, it's a consequence of, so I stated before the actual statement in Goswami's paper, which is exponential bound on the pivots, and the consequence is the following, just this, that for every delta, there exists alpha naught such that for every alpha bigger than alpha naught, there exists L, and such that the probability that the kth interval is bad, L bad means bad with this parameter, is less than delta. And this is true for every K. So it's a fairly simple bound in a sense. You just want to say that if I give you delta, and then you can choose this constant alpha, so you think about what happens, right? So what happens if the constant alpha changes? Well, the length, alpha is the length of this interval. So the length of this interval, if the length becomes larger and larger, of course, it's more and more likely that there is a pivot. However, what is not completely obvious, I think, and that's why we need definitely some form of this pivoting technique, is that the bound is completely uniform. So this is the only thing we need. So maybe it's easier to prove you don't need the full power of pivoting, but this definitely falls. And so remember, so we can play. So this alpha can be made large. So it's when alpha is large, then it's very unlikely that you don't have pivots because you have a lot of time to find such pivots. But of course, if the interval is very large, well, the second condition, the fact that the step is bounded, well, it's going to be more unlikely. So, but we choose L afterwards. So we can still choose L so that even if we have no bound on the moment, so we can really predict how long it takes for this walk to make this progress or not. But you know, you're just using this the fact that, well, this is some random, the length distribution is some random variable. So eventually you're gonna make it less than some absolute. Yeah. 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 Correct. 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 Yeah, it does get harder, but the thing is, but you have this this bound, right? So yeah, the bound is exponential. The bound on the tail is exponential. So you can sum over it. So I mean the way this doesn't happen, it means that so after this amount of time, you will backtrack all the way to here. So in the meantime, you can destroy the pivot. So you put the pivot, you go, okay, you can destroy some stuff. But you know, after 10 years, how many of your papers are found to be wrong? Hopefully not too many. So, maybe your PhD thesis would still be true. Hopefully. I don't know. Okay. Okay, so now, yeah, so okay, and so from here we just more or less just need bound. So we bound the three things separately. Okay, so what do we know about this pivotal times? Well, we know how big they could be, and we know how many there are. Okay. So how many pivotal times there are? Well, there's n over alpha pivotal times. So if you consider them independent, this will be the maximum entropy that you have. So it's n over alpha random variables. And each random variable, how big could it be? Well, each pivotal time has alpha plus 1 choices. It's a number between 0 or -1 and alpha. Right. So in each pivotal time has alpha plus 1 choices. So the total entropy that you could have is this. This is the entropy of one pivot. And at most you have n over alpha pivot. And if you consider they're independent, you get this, but in reality they're not, but the entropy is less. Okay, so this is not bad, not so good, but not so bad, because, well, alpha eventually will become very large. So this linear thing is not so nice, but yeah. The second thing would be, how about dn alpha? So the distance. Oh, that's easy, because the good distance is very good. So we impose that by definition that the step size in the good part is less than L. So the total distance in the good part is Ln. And so, well, this is at most log, or maybe let Ln plus 1 or something like this, if you want to count 0 or something like this. But anyways, it's the number of choices for the good distance is really not too many such choices. Okay. And now what about the last thing? The last thing is the thorniest one is, what about the entropy of the bad part? And for this, we need to use an elementary measure theory lemma, which tells you the following. So let's look at the position of, say, one position of the walk, or one increment. Well, what's the entropy of knowing one increment? Well, that's h of mu by definition. So this is bounded, and it's constant for each step. And so when do we try? So what is the variable that we're looking at? We're looking at the following variable, yjk, say, which is the increment gj, so the jth increment, but only if the interval is bad. If the interval is good, if the increment is good, we forget about it, we don't care. So the random variable in question is this. So this is gj, so the increment that has some entropy, but we only consider it if we know it in the bad interval. And so in the end, if you have the lemma that we need to use, coupled with the pivoting lemma, is that if you have a random variable and you only look at its value when when you're also hitting some small measure set, then the entropy of the resulting variable is small. So let me just write this somewhat exercise that you can have fun or not doing it. So the following is true. So let's look at the random variable. Let z be a random variable on some space omega into A. So A is a countable set. Okay, and we have the entropy of Z to be finite. Then for every epsilon, there exists delta, such that for every measurable set E inside your space with small probability, so if you have a small set, then the random variable, this random variable, which is Z times the characteristic function of the set E, is less than this. So you see, we only care about the value of Z if we are in this set. But this set happens to have small measure. And it turns out that the total entropy of this is still pretty small. And it's very strong. I mean, it's simple but strong in the sense that you have no assumption whatsoever on the correlation between these two things, between Z and E. So there's no, could be very bad, but it's still you can apply this. Okay, and so from here we are more or less done, because what is the entropy? So the entropy of this Bn alpha L, what is it? Well, this is the sum over J and K of these random variables y, j, k. So J is a position inside the interval ik, and k is some number less than n over alpha. And what else do we know? Well, what is the probability of this event? Well, the probability of this event is given by the pivot. Right? And so it turns out that that probability is less than delta, and then we put it in that machinery, and we find, given any epsilon, we can find some delta, so that this entropy is less. And so in the end, okay, we're done, because in the end, each of these random variables, how many positions do we have? Well, so we have n over alpha values of k. How many values of j do we have? Well, for each interval, you have 3 times alpha, actually, because we keep track of the current interval, the future, and the previous one, so 3 times. Okay? And then the entropy of each of this, well, by this lemma, this is just epsilon. Okay? And so this is, of course, 3 and epsilon. So, of course, it's epsilon times n. And so, of course, when you divide by n, and the limb soup will become less than epsilon. You think about it, what happens, right? So if you take this, you divide by n, you take the limb soup. So maybe let's just write one more sentence just to summarize. This is D and L, and this is B and alpha. Well, if you take the limb soup of this over n, well, this is the first term gives you log alpha plus 1 over alpha. Second term gives you 0. And third term gives 3. And so, of course, then we can choose alpha so that this is also small. So that basically does it, because then we've proven that this new partition has little information. So we have HG, HPN is less than epsilon n for every epsilon. And so this concludes that this guy is also less than epsilon n for every epsilon. Okay, so I think I'm done with this proof. Any more questions? Yeah. Correct. Yeah, I think so. Yeah, the point is you need to control the bad things, and the bad things, again, the geometry of these bad things, there is no way we can control, or I don't know, it doesn't seem obvious, but the entropy of it is controlled. Okay, very good. Are there other questions about this proof or topic in general? I want to, yes? Now, alpha could be large, but does not depend on n. No, but right, there is an interplay between alpha and n, but you choose them in different order. So, okay, let's discuss this later. Yeah. Okay. Good. Let's go to the next topic, which is, so the next topic was related to the singularity of harmonic measure for certain random walks and Fuchs in co-compact groups. So let me state the theorem that I stated the first day. So, okay, so the theorem is the following. And again, it's due to Poisson and myself. So the following, we start with P, a hyperbolic 2m gon. And we let P to be the set of translations that identify opposite sides. Oh, yeah, and so we want it centrally symmetric. Yeah, this is the crucial assumption. So the picture, again, we can talk about maybe octagon, which is the easiest. So this definitely need not be regular or anything like that, but you still want to impose this symmetry condition. And that in particular, the symmetry condition will allow yourself to identify opposite sides because they will be isometric. And so there is these translations like P1, P2, and so forth. Okay? Hyperbolic translations, so loxodromic elements identifying opposite sides. Okay? And then what? Then right, so then for any, right, and suppose, yeah, remember that in the Kaymanovich-Laprince conjecture, you needed that the group generated by this hyperbolic elements be discrete. So this is a subgroup in SL2R, group of isometries. And we need the discreteness. And for instance, the discreteness is given by Poincaré's theorem if the sum of the angles is the rational multiple of pi. I mean, there is a minor combinatorial condition there depending on the parity of M, but that's basically it. Okay, so then for any measure mu supported on this generating set, so nu mu, the hidden measure, nu mu is singular with respect to Lebesgue measure. And in fact, moreover, the Hausdorff dimension, as I defined before, so which is given by the local scaling of balls, is strictly less than 1. So again, the topological dimension of the boundary is 1, but the dimension that of the measure that is stationary for this walk has strictly less. Of course, 1 implies, so this claim implies the previous one. And in fact, it turns out that they are equivalent by previous work. So in some sense, it's just as hard to prove one than the other. Are there any questions about the statement? Yeah. Right, so the assumption about the angles is hidden in here. It's actually pretty easy. It's just that the sum, so if you call these angles gamma I, the sum of the gamma I, the even ones is 2p over k, and the odd ones, and yeah, and also the odd ones. So there's two cases. If M is even, like an octagon, they're all in the same class. If M is on, like the 10-gun, there's two different classes. So that's why you have to, you possibly need to. 2 pi over k. Yeah. K is some integer, yeah. Yeah, because when you identify here, you can go multiple times before, right? The tessellation you can go around once, or you can go around more than once. No, I think it's still a surface. Right. So you get orbifold if you have less than 2 pi. Yeah. Yeah, sure. No, you're right. Yeah. Anyways, this is literally the application of Poincaré's theorem. So whatever it is. So for simplicity, let's assume that the sum is 2 pi, so that we don't just for this proof, but yeah, it doesn't. Okay, so the idea. So okay, so there's two words here that we're comparing. And so the main idea is to compare, yeah, in a sense, so compare the probability with the geometry in some sense. So we have this abstract group, the abstract Cayley graph, and it has a measure on its boundary, which is given by the van der Waals. On the other hand, this group is embedded in the isometries of hyperbolic space. So the hyperbolic space carries a hyperbolic metric. And obviously, the Lebesgue measure is, for instance, the Patterson-Sullivan measure in this case for this hyperbolic metric. In any case, it's a natural geometric metric, which. Okay. So the idea is to compare two metrics on G, given by, one is by probability, and the other one is given by the geometry. By the way, let me say that if we replace the hyperbolic metric with the word metric, then this conjecture is completely solved by Guzel, Mathéus, and Macourin that prove that the corresponding quantities are equivalent, are in the same class if and only if the group is virtually free. So this, of course, would be a surface group, so it's not free. so that would be the case. But here we don't care about the word metric. So here we care about the geometry of hyperbolic metric, which again is quasi-isometric to the other one, but it's not good enough that they're quasi-isometric to really tell them apart. I will. So okay, so the definition of the green metric, yes. It's somewhat very simple. So you want to, it's a metric which depends on the geometry. Say you want to go from E to G. What you do is you look at the probability of ever existing a path, random path, that goes in n steps from the identity to G. So the probability of ever in however many steps reaching G. And this is a number, of course, between 0 and 1. So you want to metric-like object, you do minus log. So that's between 0 and infinity. There are different definitions of this green function, but they're all equivalent up to a multiplicative constant. So then they are equivalent up to additive constant in this case. Okay, and so the main technical ingredient that we borrow here is this characterization of Blacher, Isinsky, and Mathieu, which is the following. So you look at gamma as the hyperbolic group. So let's say it's a group that acts properly, discontinuously, and co-compactly. On delta hyperbolic space, hyperbolic proper, of course, space, proper space X. Okay, and yeah, let mu a measure. Actually, it's enough to have exponential first moment, but okay. Finite exponential moment. In particular, if it's finally supported, is fine. Okay. So the following are equivalent. So first of all, is that the hit-in measure for this random walk is in the same class as the Hausdorff measure. So let's call it H alpha. Alpha, where alpha, so Hausdorff measure. Alpha is the dimension of the boundary, or the boundary axis, which is, yeah, should be the same if you have, no, it's not the same. No, the boundary axis. So the second is that there is this inequality that I will write in a second is an actual equality. So the H equals L times V. And the third one is that there exists C such that the hyperbolic distance and so the ambient distance and this green distance are the same up to an additive constant. So in this case, we need to say something like this. Okay, so, and what are H, L, and V? So H we already saw, and L is also. So H is the entropy. So it's the limit of H mu n over n. L is the drift, the limit of the x O W n O divided by n. This exists almost surely. And then V is the volume growth, or yeah, growth rate. So is the number of elements in a unit ball, or in a ball of radius n. So G is the distance. So whenever you have random walk, well, you can associate its entropy. This only depends on the group. There is no metric space here. You can also have, whenever you have a group action, a growth rate of the action, which is, again, only depends on the geometry. And this one sort of mixes the geometry of the probability because this is just the speed of the random walk according to this metric. And then there is this inequality, which is being called by Vershik fundamental inequality, which is, again, a convexity inequality. It's kind of like Jensen, is that H is always less than L times V, as soon as these three quantities are finite. So for instance, it's enough to assume that, you know, the volume growth is finite and that it has some moment condition, for instance, finite first moment, such that this is also. So in fact, this is true for every action on any metric space. As long as these two things are finite, then you have this inequality. And in fact, so this inequality goes back to Ghosh, I think. And then it was, you know, more popularized by Vershik in the sense that he called it the fundamental inequality. And he started asking in various questions, various settings, when this inequality could be an equality. And in fact, in this situation, when you have a co-compact action, well, it turns out that this V is related to the topological dimension of the boundary, and the Hausdorff dimension of the measure is H over L. So in fact, the same thing you could say is that the dimension of nu mu equals the dimension of the boundary. Yeah, because let me also remember the following factor, proposition or something, that the dimension of this hidden measure is H over. And so this is due to Le Drapier. If you take a weaker definition of dimension, or Tanaka if you take a stronger. Okay, any questions? We need to digest this. So this is the two measures are the same up to measure class. This is the two measures have the same dimension. And this is the two metrics are the same, not just up to quasi-isometry, but okay, if we forget about this factor, is they are the same up to an additive constant. So in fact, in our case of a co-compact Fuchsian group, V would be 1. So you don't really care about that, and they would just want to show that these two metrics, one coming from the geometry and the other is coming from a probability, they are not bounded distance of each other. Questions, comments? Yeah. Right, okay, yes. So the metric on the boundary of the hyperbolic space, yeah, is defined up to so-called snowflake equivalence. So you have this epsilon. I just assumed epsilon to be 1 here to avoid yet another parameter. But of course, if you rescale the boundary metric, all these quantities will be rescaled by epsilon. So it's just yeah. But if you take just a hyperbolic plane, then clearly the natural metric is the Lebesgue one. You're not going to snowflake the standard circle. But in general, when you have a group, then yeah, of course, you have a one parameter family of metrics, and you just have to rescale things accordingly. Yeah. Okay. So now let's see how the proof goes. So there's not, let's say we can break down the proof in maybe 4 lemmas. And the idea is to break down the probability and the geometry in 2 parts. So first of all, let's start with this crucial observation, which is the following. So you suppose that the measure nu is absolutely continuous. Then, for every g in G, I claim that we need this inequality, L of G is less or equal than the green metric. And what is L of G? L of G is the translation length in the hyperbolic metric of this element. Right, in the picture, recall that we have this oscillation. We have the translation length is, in this symmetric case, is basically the distance between the midpoints of opposite sides. because this is a hyperbolic element that preserves this axis. And another way to think about it, which will come used for secondly, is that if you project this down to the quotient surface, you got a closed curve, which in this particular case, I don't know, it's definitely not this one. It's some curve, which, yeah, probably someone should know what it is, but I'm not sure. But anyways, it has some curve that has a certain length. L of G would be the length of the group element. Okay, so the proof of this is fairly simple if you think about it. So what happens? So if not, well, L of G is bigger than the green metric. So there is a gap. However, the idea is that if there is a gap, you take powers and your gap grows. But if the gap is too big, it would contradict this. So it's very simple. If you look at L of GK minus d mu 1 of GK, well, this is bigger. So L of GK is KLG by definition. And by the triangle inequality, this is less than K times d mu 1G. So the green metric does satisfy the triangle. And okay, this one is just because we are preserving this axis. So okay, here we're somehow using this additional structure, but the distance in hyperbolic metric between 0 and GK of 0 is precisely that. So why is this bad? Well, you can see, because this gap is bigger than K times a constant. Of course, as K goes to infinity, this constant goes to infinity. And this clearly contradicts this point. The simple idea. So the thing is, since the situation, the polygon is not regular and the measure is not uniform, we cannot really say, okay, this particular, so the idea is, you see, if you have an element with large translation length, this contributes to the measure being more singular. We call also that the dimension is H over L. So if you take an element with very large translation length, this L will be very large. So this dimension tends to be small. So this is good. However, you can change the shape of this polygon. And so the idea is there has to be some mechanism that tells you that okay, this generator somehow balance out in a way that there's at least one which is long enough. Let's say. And so what is the geometric idea? Let me first tell you what the geometric idea is, and then I'll tell you the probabilistic lemma. So this is an interesting fact in itself. It's a purely geometric inequality. Is the following in the following sense. So if E is given by T1, T2M, right? As above, so they generate this discrete group, then the sum of 1 over 1 plus e to the length of Ti from Y to M is less than 1/2. So this is a purely geometric inequality. So this has to do with lengths of curves in a hyperbolic surface over a finite set of lengths. Now, if you ask a geometric topologist or, I don't know, Higgs-modal theorist or three-manifold person, what does this remind you of? Yeah, so there's two things. There is one is even older than that, is the Köhler-Schelen inequality, which in fact was improved slightly by Anderson, Canary, Feller, and Shalen. So this is literally the same inequality for a finite set, but this is for free Kleinian groups. So it's in H3 and not in H2, and it's for free groups. Our group is not free, is surface group. So in fact, this inequality, the R version is in a way stronger because the translation lengths are shorter in the co-compact case. But it's the same form. The second one, as everybody said, is the McShane identity, and then was, of course, generalized by Mirzakhani in a much greater generality. But let's stick, for instance, to the McShane one. So what McShane did is for a puncture torus, so he gets equality when you sum over all simple cross curves. So here we only sum over some finite subset of them. The group is also another group, it's not the puncture torus group. So they're different, but still it has exactly the same form. So I don't think this implies the other ones or vice versa, but it's curious that eventually they have the same. And so what is the main idea here? Geometric idea. So I'm not going to prove this because it does use hyperbolic trigonometry, in fact. But what is the main idea about this is a color lemma, basically. It's a much more sophisticated version, but the geometric principle is the color lemma. So what does the color lemma say? Well, it says that if you in a hyperbolic surface, two short curves do not intersect transversely. And so in particular, and this is true in these curves are intersecting by design, right? So the idea is that if you have octagon like that, this would mean that there's a short curve, let's say Ti. Right. So, and this would be bad because if this goes to 0, this term gets close to 1/2. So if you had another short curve, this would not be good. But the way this generating set is chosen is that, okay, the other ones would be transversal to it. And so they would intersect. So if this one is very small, the other one has to be very long. And of course, well, it's not an immediate application of the color lemma. You really need hyperbolic trigonometry, but eventually you see that these things balance out. Okay, so then I need two more lemmas, which are simple enough that probably I can present both. Okay, so now let's look at the probability. So we don't know, it's slightly more complicated to control the surface group presentation, but we can definitely control random walks on free groups. So suppose we have our good old random walk on free group. And suppose we take a nearest neighbor random walk, so not necessarily simple, but just nearest neighbor. So you go only step 1. So yeah, so let mu be nearest neighbor random walk on some free group. And this case is a free group on M generators. So you have 2M valence for the tree. And let xi be more or less this first passage function, so the probability that at some point your random walk is going to end up in the generator I. So this we generate Fm as A1, Am. Now, and okay, for simplicity, let's assume it's symmetric. We don't need it, but otherwise the equation is a bit more complicated to write. So now here's an exercise in probability that maybe you've done if you've taken a course in I don't know, probability on graphs, is the following, that xi divided by 1 plus xi, where I equals 1 to m, this is equal. And the proof of this actually can be given because it's a fairly elementary result on trees. So what is the proof of this? Okay, so we want to measure the probability of ever going from this side to this side. So this is A1. Okay. So what do I claim? I claim that nu mu of the cylinder of AI is xi divided by 1 plus xi. So what is the cylinder is also what I call the shadow, is just all paths that start with A1. Or geodesics that start with it. Okay, so now what is the proof of that? Well, so how can we measure the probability of hitting this cylinder? Well, how do you hit the cylinder? You start here, eventually you have to go there. However, if you cross again, this is not good. You're not gonna converge into here. But you can cross once, do some stuff, cross back, do some stuff, cross again, and do some stuff. So you have to cross an odd number of times. So this is the probability that the random walk crosses AI an odd number of times. Okay, and so we can do the calculation. So this is a tree. So the first passage function is multiplicative. So we go from here to here, you got xi. And now what we could do is we can go from here and never go back. So that would be 1 minus xi. Or we can go, come back, and go again. So this would be 3 times. And then again, not crossing once again, and so forth. So this gives you all the odd ones. Yeah, and then you just, right. So this means you cross 3 times, and then you don't cross after. And then, of course, this is clearly this. Okay. And so once we have that, well, we can conclude the equality. Why do we conclude that we have the equality? So we found a formula for the measure of one cylinder. And then what do? We want to prove this identity, right? Yeah, we just sum over all cylinders. So this is a free group, so the cylinders are disjoint. So you don't have these problems. So by summing, what do you get? You get the sum of xi over 1 plus xi is the sum of the cylinders. And okay, we took just from 1 to m, otherwise we take everything twice. So this would be half of the total probability by this symmetry. But again, if there's no symmetry, you can do something slightly. You get a slightly different equation, but It's just slightly simple. Okay, so now we have, so the idea is we have a geometric inequality that tells us that this geometric metric, you have to have some long element. You don't know which one, but some. On the other hand, the probability tells you that you have this preserved quantity. And so then we are ready for the final proof, the proof of what I called theorem A, I think, at the beginning, is the following. So suppose nu mu is absolutely continuous. Well, then by dilemma, then there has to be a generator for which its geometric length is bigger than this probabilistic metric. So let's call it Ti. This is the original lemma. Is it this way or the other? No, it's sorry. Yeah, it's the opposite. Sorry. Then for every I, it's like this. Right? And so, okay, and then we want to compare these two things. So how do we compare these two things? So we consider the following homomorphism. So we take just the free group in M generators and we map it to our surface group. So we consider some, abstract generators, and we map them to our generators that we had before. And then we define a measure of mu on Fm, given by mu tilde of AI, just mu of Ti. So we lift the walk from G to Fm. This is a homomorphism, so there is no problem doing that. Of course, the green metric is not preserved, but you note that green metric is one Lipschitz. When you have homomorphism for homomorphism. This is not hard to remember. So the green metric could go down, but fortunately it's fine. Yeah. So yeah, because what happens? Well, what happens is that L of Ti is less than d mu, E Ti is less than d mu tilde E AI. And this guy, by definition, is minus log of xi, where xi is the first passage function on this. Yeah, and then it's just calculus. So hopefully we can do the calculus. E to the minus L Ti is bigger than xi. And so if we compute, we go this function, we look at xi over 1 plus xi. Yeah, maybe let's write it this way. So xi over 1 plus xi is less or equal than e to the minus L Ti over 1 plus e to the minus L Ti. Then we sum over all possible i's. Yeah, this is exactly the quantity that we have in the geometric inequality. And then we clearly see what happens. On the one hand, the probability tells you that this has to be 1/2. On the other hand, the geometry tells you that it is strictly less than 1/2. So then you clearly get a contradiction. Okay, so that's the end of the proof. Thank you.
Any questions, Giulio?
Yep. free groups. Yeah, but free groups acting on itself. That's free groups are maybe virtually free as well, but yeah, the inequality is, yeah, that's right. So they are equivalent. So yeah, that's right. So as I'm saying, the only place where we know it's equal is do we have a free group acting on itself. This is the big conjecture, right? So the conjecture is that for co-compact groups of hyperbolic manifolds, you never get equality. Yes. So the only equality is that you know, yeah. So actually, if you have a not discrete group, I don't think you can apply the HLV machinery. So there is this examples by Bougan, but the action, the image is non-discrete in SL2R, so I don't think you can apply on the nose the HLV, this inequality. But as I said, if you replace the hyperbolic metric with the word metric, so you get a different L. So as you want to say H equals LV, so we know always like that. So of course this depends on D. So here we looked at the hyperbolic one, which of course is less than the one where we look at the word metric. Yeah. And so it turns out that, yeah, if you look at when this is an equality, okay, that is a different problem that is completely solved for word metrics. And in that case, the only case is the virtually free group acting on itself. But if you act on a hyperbolic space, the problem is really that it's hard to estimate these two metrics. Mm-hmm. Right. So our proof is not as you could guess is not constructive. As I said, in principle, so there is a way that you could try, which is by looking at thermodynamic formalism using the Bowen series coding. And then for a specific case, you could get an estimate on the yeah, so it looks like, so the thing is, yeah, so what is the maximum of, for instance, if you, yeah, of a sort of moduli space? This is a very good question. So it's a recent claim paper that, you know, if you go to the boundary of diagonal space, then this dimension goes to 0, but then in the middle, you know, the max should be conjecturally the most regular example in some sense, like a regular octagon, for instance. But okay, we can estimate the one for the regular octagon, but then, of course, we don't really know what happens.
So if there are no further questions, let's thank Giulio again for this wonderful series of lectures.